Are you scared of artificial life, artificial intelligence?
Um,
Elon Musk scared the shit out of me
yeah,
when he talked about it. Like he talks about it like we're in the opening scene of a science fiction movie where he's trying to warn people, and then they don't listen to the genius, and it goes south.
sort of depends. I chaired a debate on this with the Royal Society in London a few weeks ago, and so it's true now at the moment. What people tend to be frightened of are general AIs, or AGI they call it, artificial general intelligence, which is like what we talked about earlier, a human-like capability. There's a theory called eternal inflation, which is a theory that, and it's actually the most popular theory I think at the moment for what happened, for why the Big Bang is the way that it is. Because it's got some very special features, the Big Bang, which we could talk about. But inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. And it was doubling in size. So it's an unimaginably fast expansion. And then the idea is that draws to a close. So it quite naturally sort of dies away and the expansion slows down. And all the energy that was taken, that was causing that expansion, sort of gets dumped into space and heats it up and makes particles. And that's what we call the Big Bang. And those theories, the slight extension to those, say that slowing down just happens in little patches. So most of the universe, the overwhelming majority of the universe, is still inflating at that insane sort of speed. And just little patches stop and they're Big Bangs. So you get multiple universes, a multiverse. It's called the inflationary multiverse. And we are in one of those bubbles. And that's one of the more popular theories.
Why is it that we think that the known universe is larger than we can observe?
The best way to explain the universe, the properties that we see, is that it's very much bigger than the piece we can see. So, for example, we measure space to be what's called flat. And that's a very unusual thing for it to be like. It requires, because what Einstein's theory says is that the shape of space, that the curvature of space is determined by the stuff that's in it. And what we find is that there's precisely the right amount of stuff in the universe to have a completely flat universe. And the explanation, the most favoured explanation for that is the universe is way bigger than the piece we can see. And so it's like looking at a piece of the Earth. If you look at a little 1 mile square of the Earth, right, then it's flat, right? You have to look at big distances, kind of order the radius of the Earth, to see that actually you're on a curved surface. And that's one of the ideas about the universe and why it appears to be the way that it is, because it's way, way bigger. So we're just looking at a little piece. And that's why it looks flat.
Is it possible that in the future we'll be able to see past 13.8 billion years?
Not with light.
Not with
because
light.
What the picture is that before, it's actually was released 380,000 years after the Big Bang. It's a very precise number. You might say, how do you know that? Well, before that time, the universe was so hot that atoms couldn't form. So you had a soup of electrically charged particles. It was just too hot for electrons to go into orbit around nuclei. So the universe was opaque to light. So you just couldn't, it was like almost like a big glowing star, if you like. And then when it was expanding, it cooled past the point where the atoms could form. And at that point, it becomes transparent, really almost instantly in a cosmic timescale. And so the light could then travel in straight lines through the universe, and we can see that light. So we see the light from that time, but further back than that, it's opaque, so you can't see past that. In The Brief History of Time, Hawking says, well, imagine bouncing a ball. So we bounce a ball on the table now, a tennis ball. So I drop it and I catch it again. So let's say I drop it and it takes a second to bounce up. So in that second, the Earth has moved about 18 miles or so in space around the sun. So you could ask the question, did that ball return to the same place in space or not? And the answer is, you can't answer it. It does from our perspective, but from the perspective of someone watching the Earth go all the way around the sun, when I caught it again, it had moved 18 miles. And then from some other perspective, it would have done something else. So the point is, you can't say this is a point in space. It came back to the same place, because that just depends on your perspective. It depends on whether you're watching the Earth go around the sun or whatever it is. So Einstein said that means there's no such thing as absolute space, which kind of follows if you think about it. But that's a difficult, it's a cool but difficult thought process. We don't know all the answers, so we don't know where the laws of nature came from. We don't know why the universe had a beginning. So we don't know why the Big Bang was very, very highly ordered, which is really the reason that we exist. That's the reason, because the universe began in a particular form. Science provides a framework framework within which, if you want to philosophize or you want to do theology, it's just an observational framework. We understand nuclear physics. We can build nuclear reactors, for example. So we understand the physics of stars. We understand that the stars built the carbon and oxygen. One of the great things about cosmology is that it is terrifying in the truest sense of the word. I mean, we talked a bit about the size and scale of the universe and black holes colliding and those things. It is very frightening, but also I think the act of trying to understand our place in nature and the size and scale of the universe, tiny presence within it, is valuable, so that you can be terrified but also inspired and interested. If you want to ask questions about what it means to be human and means to be alive, then I think you find the answers in confronting that reality, which is that we live in a terrifyingly vast universe. Einstein had a theory that suggested that the universe is just not static, and actually it really strongly suggests that there's a beginning. Georges Lemaitre, who worked independently of Einstein but at the same time in the early 1920s, before we even knew there were other galaxies beyond the Milky Way, and they noted the equations suggest the universe might be stretching. And so he wrote to Einstein and said, your theory suggests there was a day without a yesterday, because he thought if everything's expanding now, then it must have been closer together in the past, and so there might be a time when it was all together. And he was a priest. So he's a Belgian priest. And Einstein tried to dodge it and put this allowed term into his equation, which is almost a stretchy term, so it can be eternal. You can't make it eternal that way. But so he tried it, then he took it out and called it his biggest blunder. So learning to live and work in space is, I think, a natural extension of our civilization. Plus the fact, if you talk to Elon or Jeff Bezos, they point out the amount of resources available just slightly above our heads is vast. Now, we don't want to do that, but his point was that the energy from the sun is all up there, the resources are up there. So you could almost imagine trying to zone the Earth residential at some point in the future to protect the planet and do your heavy industry off the planet, for example. It sounds like science fiction, except that now SpaceX and Blue Origin, those people have got reusable rockets. So suddenly the economics become sensible. I think expansion is good, and I think we will expand, and I think we will expand outwards, because there's not much room left on this planet to expand. That's a whole different idea. It's not about gathering scientific information. It's about a frontier and all the benefits that come from operating as a civilization on a frontier. They've been observing collisions of black holes. So you can imagine how extreme, like a colliding black holes. It's an incredibly extreme event.
So this collision of black holes, the idea that you can detect that.
The first paper they published, there are two black holes and they were about 30 times the mass of the sun each, and they were orbiting each other, and they accelerated. At one point they were approaching each other at 1/3 the speed of light, and they accelerated to 2/3 the speed of light in 1/10 of a second, and then hit each other. And the explosion, the energy release, I think I'm right, it was something like 50 times the energy release, the power of all the stars in the observable universe glowing. It's an unimaginably violent event. Stephen Hawking actually and some others before he died had this idea called breakthrough starshot, which is the idea to send a little probe out to the Alpha Centauri system. And I think in their view, Yuri Milner as well, the entrepreneur, wanted to do that. And I think it's something like 100 years travel time or something with our current technology. And they pointed out that we don't do that now. We don't think 100 years in the future. But if you go back when people were building cathedrals, people used to routinely start projects that would take 100 years to bear fruit. Yeah. And so we could imagine going there. And that then becomes fascinating, I think, because then you've got a solar system, another solar system that you could go and visit conceivably. Plus the fact, if you talk to Elon or Jeff Bezos, they point out that the amount of resources available just slightly above our heads is vast. And so I remember I talked to Jeff Bezos actually once, and he thinks really simply, and he said, for example, in the asteroid belt, there's enough metal, I think, to build a skyscraper. What is it? It's something like 800 stories tall, and cover the Earth in it, right? If you want. Now, we don't want to do that. But his point was that the energy from the sun is all up there, the resources are up there. So you could almost imagine trying to zone the Earth residential at some point in the future to protect the planet and do your heavy industry off the planet, for example. And it sounds like science fiction, except that now SpaceX and Blue Origin, those people have got reusable rockets. So suddenly the economics become sensible. So I think expansion is good, and I think we will expand, and I think we will expand outwards, because there's not much room left on this planet to expand. If you think about what the job of a scientist is, stand on the edge of the known, because you're a research scientist. So if there's nothing to know, then you've got no job. Right. So you have to be naturally comfortable with not knowing. And if there's one thing I really do think, how do we begin to patch our countries back up again? One of the reasons I think in education is to teach people the value of uncertainty, of not knowing. It is not weak
Right.
to not know. It's actually natural not to know
And that's
not
one
be
of the
afraid
problems
of it.
with religion, is to say that you know when you do not, or to say that you have absolute truth and absolute knowledge of something
Yeah.
when it can't really exist.
Yeah, I mean, history tells us, doesn't it, that you know,
Yeah.
anyone who thinks they've got absolute knowledge causes trouble.
Yeah. Did you see Ex Machina?
Yeah.
Did you enjoy it?
Yes, I know Alex Garland because he
Oh,
wrote
do you?
Sunshine. It's one of the arguments often used to say there aren't any civilizations out there in the galaxy, called the Fermi paradox. Because if you imagine a civilization that's a million years ahead of us, they should have written their presence across the sky by now. You should see them. I mean, you'll see us. If we survive a million years into the future, actually even a few thousand years into the future, we will be exploring the galaxy. We will have spacecraft that are going to other stars. We will be doing it. So our signature will become visible, I'm sure, if we last into the medium term.
Would we choose to not do that? Here's my thought on that, is uncontacted tribes. Like, do you know about the gentleman who was the missionary who visited North Sentinel Island and was killed by the natives? North Sentinel Island, which is a really unusual place because they branched off from Africa 60,000 years ago, and they've been living on this one small island the size of Manhattan.
What is true about Mars, it's interesting actually, because we know something about the history of Mars, quite a lot about the history of Mars. And it's certainly clear that there was water, almost certainly oceans, rivers. And that water is almost certainly still there. So I would say certainly still there.
Well, they have found large quantities of ice now, right?
Yeah, so there's certainly ice. There may even be pockets of liquid water below the surface somewhere. So couple that with all the minerals and the resources that we know are there, and you have everything you need. So that's the thing about Mars. It's quite nice relative to everywhere else other than the Earth. You can't go to Venus, right? You just melt. It's, 400 and something degrees and 90 atmospheric pressure.
Yeah.
So Mars is quite nice, but I wouldn't go there. I agree with you.
What's the gravity of Mars in relationship to the Earth?
It's about a third, I think.
The way that the Earth will end ultimately is as a cinder, right? Because what's going to happen is that the sun, in about a few billion years' time actually, but it's going to start growing as it gets older, and it'll swell up. Probably won't engulf the Earth, but it'll get close. Right? The Earth will probably drift out because the sun will lose some mass. So but it'll toast it basically. So the Earth will end up toasted as a cinder, probably still orbiting the remains of the sun, which will be what's called a white dwarf star, which is just something that basically fades away. What we do now is we look for them quite sensibly. So we map the orbit, the big asteroids, we've got most of them, we think, that cross the Earth's orbits, and we monitor them all the time. And we have what's called a keyhole system, and it says that if one of these asteroids goes through this point in space at this time, then we're worried about it, and we'll be very careful and we'll watch it. So we're watching them, and if one goes through the keyhole, then what you need to do is nudge it a bit so it doesn't hit the Earth. And the DART mission was the first mission designed to make sure that if we really want to hit an asteroid with something, then we can do it. And it's hard. And so we did it. It was a very clever mission because it's a double asteroid system. So the little one, that one of them was hit, so there's two of them going around each other. And we hit one of them, and that means that you can measure the orbit afterwards of these two things. We know that the dinosaurs, other than the birds, were wiped out by a big asteroid impact 65 million years ago. We know that. So occasionally big pieces of rock hit the Earth, and occasionally those big pieces of rock are big enough to cause mass devastation. What we do now is we look for them quite sensibly. So we map the orbits of the big asteroids, we've got most of them, we think, that cross the Earth's orbits, and we monitor them all the time. And we have what's called a keyhole system, and it says if one of these asteroids goes through this point in space at this time, then we're worried about it, and we'll be very careful and we'll watch it. So we're watching them. And the DART mission was the first mission designed to make sure that if we really want to hit an asteroid with something, then we can do it. And it's hard. And so we did it. It was a very clever mission because it's a double asteroid system. So the little one, that one of them was hit, so there's two of them going around each other. Then we hit one of them, and that means that you can measure the orbit afterwards of these two things orbiting around each other to see how much we deflected it. So it's a smart thing to do.
What is the most likely way that the world could end?
What's going to happen is that the sun, it'll grow as it gets older, and it'll swell up. It probably won't engulf the Earth, but it'll get close. The Earth will probably drift out because the sun will lose some mass. So but it'll toast it basically. So the Earth will end up toasted as a cinder, probably still orbiting the remains of the sun, which will be what's called a white dwarf star, which is just something that basically fades away. So that's what's going to happen in about 5 billion years. If you mean by the end of the world, you mean the end of civilization, then long before that, we'll have had to escape, because it will become the conditions on the planet will not support complex life like us. It'll be too hot. We might not have to wait for the sun to do it, because we might do it through our own stupidity.
The best Einstein prediction, we discovered a thing called a double pulsar, which is two stars, the mass of the sun, compressed into something about the size of LA. So imagine the mass of the sun into something the size of LA. They're rotating around each other about once every 2 days. One of them's spinning 40 times a second. The other one's going around once every 2 seconds. And Einstein predicts that they fall into each other at a rate of 7 millimeters a day in 1916. That theory.
1916
That's
makes
a
his
theory.
prediction, right.
And a few years ago, we find this thing, we do the measurement, and we find out it's true. These things, these two stars, drifting in at 7 millimeters a day in perfect accord with the
So all these
predictions of
years,
Einstein.
60 years after his death, you find out that he was absolutely right about something. One of the biggest discoveries in science in recent memory, the Higgs particle.
Yes.
Of what the Higgs particle is.
It's the most beautiful, ridiculous story. The prediction, which dates back to the 1960s, is that sometime after the universe got to the size of a melon, and remember, the universe today has got 350 billion galaxies in it, each with 100 billion stars.
Yes.
Once upon a time, it was the size of a melon. Some point after that, it was expanding and cooling, and something crystallized or condensed out into empty space, almost like maple syrup or something. The universe gets filled with this stuff as it cools. And today, now, we are massive, we are solid, because our particles are interacting with that cosmic treacle, or whatever you want to call it.
So you're saying that all the particles in the universe need to be held together by something, and this is the glue, if you will, that's holding everything together.
In a way, you get mass. So these particles are solid because they're interacting with this stuff, except for light, which travels at the speed of light because it doesn't interact with. Prediction from the 1960s, a mathematical prediction. Then, about 10 years ago, we decided to build the biggest scientific experiment ever built, 16 miles in circumference underneath Geneva. We accelerate protons, which are these simple particles, to 99.999999% the speed of light, at which the speed they circumnavigate this ring 11,000 times
You
a
get
second.
them spinning around this ring really fast.
One the other way. We collide together, 600 million of these every second. In every collision, we create the conditions that were present less than a billionth of a second after the Big Bang. We take photographs of those 600 million collisions per second, and we find out this guy from 1965 was right, which is, I think, one of the most remarkable achievements.
Assisted with one of the biggest discoveries in science in recent memory, the Higgs particle. Is that correct?
There's a prediction from the 1960s, a mathematical prediction. Then, about 10 years ago, we decided to build the biggest scientific experiment ever built, 16 miles in circumference underneath Geneva. We accelerate protons, which are these simple particles, to 99.999999% the speed of light, at which the speed they circumnavigate this ring 11,000 times
You
a
get
second.
them spinning around this ring really fast.
One the other way. We collide together, 600 million of these every second. In every collision, we create the conditions that were present less than a billionth of a second after the Big Bang. We take photographs of those 600 million collisions per second, and we find out this guy from 1965 was right, which is, I think, one of the most remarkable achievements. The best Einstein prediction. We discovered a thing called a double pulsar, which is two stars, the mass of the sun, compressed into something about the size of LA. So imagine the mass of the sun into something the size of LA. They're rotating around each other about once every 2 days. One of them's spinning 40 times a second. The other one's going around once every 2 seconds. And Einstein predicts that they fall into each other at a rate of 7 millimeters a day in 1916. That theory.
1916 makes his prediction, right.
And a few years ago, we find this thing, we do the measurement, and we find out it's true. These things, these two stars, drifting in at 7 millimeters a day in perfect accord with the
So all these
predictions of
years, 60 years after his death, you find out that he was absolutely right about something. In our lifetime, what's more likely, teleportation or time travel? Are they possible?
We can do both. We've already done teleportation. It's been a prediction of quantum theory for decades, and we've done it with small particles, so single particles. So the question is, can you do it with bigger things? Don't know is the answer. But it's been done with the smallest particles.
Is it possible that in my lifetime, instead of driving home for a long time on the freeways of Los Angeles and really losing my temper several times and stopping the car in heavy traffic and getting out with a broom handle and hitting another car, that I will get into a cube and be like, nothing will happen, I'm just doing this. No. And then I will be teleported into to my home?
I don't think you're going to have to do that today. But,
No, I want to. I like to.
For all we know, it's been done with single particles. We don't know. Time travel, it's been done in the sense that you can travel into the future. as fast as you like.
You've agitated or angered Deepak Chopra. What did you do to get Deepak Chopra so angry?
I just tweeted some fact. And he tweeted back saying, I'm going to shove my cosmic consciousness up your ass. I said to him, I call him the diamond-encrusted guru. Because when he was on, did he have his diamond-encrusted
He
glasses?
always wears, I think we have a photograph of him, he always wears glasses with jewels on them.
I know, so I called him that. And he
You
said...
called him the diamond-encrusted guru.
Yeah, and he said, it's not, they're rhinestones.
Yeah.
So, okay.
He said they're rhinestone?
I mean, yeah, he did.
Yeah.
He did, that's what he told me. But
Did you feel that was better or worse?
What do you think? You
Don't
him on
pull
the
us
show,
into your
don't you?
Deepak.
Yeah.
Wind
He's
him up.
probably coming back here someday.
Yeah.
Prod him a bit next time. Just give him a little, just say, just ask him about the Schrödinger equation. So he's talking about quantum healing and these things. So solve the Schrödinger equation in a spherical symmetric potential first. Ask him to do that. Give him a blackboard.
Wow,
See what
that's a
happens.
good slam.
We're now entering the mysterious dark frontier. Uranus, the magician. It's a planet you can see some surface features. It's a blue planet with white high-altitude clouds. And also 4 moons are visible in this BLT image. The image looks odd, though, because the moons are aligned vertically. The planet appears to be tipped up on its side. That's one of the most mysterious things about Uranus. It orbits the sun with its poles leading the way. But there are very powerful winds there. The winds at the equator move at 200 miles per hour, but in the opposite direction to its spin. Very strange. But as you move up through the tropics towards the poles, the winds reverse direction and blow in excess of 500 miles per hour. Jupiter is a creator and destroyer of worlds. We got our first pictures of the planet, and particularly the moons, from 2 iconic spacecraft, Voyager 1 and Voyager 2. These spacecraft were launched in 1977. They arrived at Jupiter in 1979. We are still in touch with them both today, 41 years after they were launched. On Valentine's Day 1990, as it was on its way out of the solar system, it took what I think is the most famous image, certainly of Earth in the history of space exploration, when it was 4 billion miles from home. It's called the pale blue dot image. Now, there are coloured stripes crossing the image, which are lens flare. If you look carefully, in a red stripe, you'll see a point of light, which is our planet, the Earth. When you look, it's called the Andromeda Galaxy. And if you know where you're looking, you can just catch it out of the corner of your eye. If you think about it, you're seeing that as it was 2 million years ago.
Yes, although
Because it takes the light 2 million years to travel.
I don't like being late to information, so that makes me feel very out of date.
Well, it's remarkable. I mean, it began its journey before we had evolved on Earth. So in the time it took, and that's the nearest neighbouring galaxy, the Webb looks so far out that it's capturing light that's been travelling for over 13 billion years. But the universe has been expanding, and so the light has been stretching. And so for the most distant galaxies, we're looking back in time almost to the Big Bang. Then the Hubble was not sensitive to that light. So that the Webb can see the formation of the first galaxies. It's essentially looking all the way back to very close to the beginning of time. And that's very important because we're not entirely sure exactly how those first galaxies formed.
So real giants could only be on a small planet.
Probably. Weak gravity, then you can grow to a larger...
But you wouldn't get a lot of them because there's not a lot of space. It's got to be bigger than the girl in the Crankies.
So the mini cranky
Yes,
planet
bigger
is
than
not,
that.
You're not interested in that at all?
No, anything bigger than that.
Kepler 19G probably is mini cranky planet. Depends on the gravitational field.
You could
If
just
it's a
be making this up.
If it's a big, huge planet, a big, massive planet, intense gravitational field, then the people will all be little.
What?
Yeah, because you're as big as you can be without the
I don't
gravitation.
think you know what you're talking about
I'm
sometimes.
just making this up. No, but yeah, there could be a cranky planet.
So if you're saying
Just a
the
little-
really big planet, the little people, well, a really small planet, that big, one really big bloke, really you know what I mean? That makes some sense to me.
20 billion Earth-like planets that could harbour life in the Milky Way. 20,000 million other Earths out there.
So there must be life out there.
Well, you would think so. The huge question now is, can we find microbes somewhere? We might find them on Mars. We're looking really seriously to see if there's life on Mars. But
No, we know there's not life on Mars.
we don't.
But not proper life. I mean,
the huge question is why we haven't seen evidence of another civilization.
do you think it's out there? You think it's out there, don't you?
I think simple life, so microbes, we may
Not
well
that, we're
find
not
on
back
Mars.
to that again. No one cares. talking about
imagine-
something
no.
with fins and a scar, like language. You know what I mean? Like whoop, whoop, whoop. We want aliens.
Well, this has got a name called the Fermi paradox after the physicist Enrico Fermi. The galaxy's been around for almost the entire age of the universe, 13 billion years.